So first of all, a disclaimer, because I'm still employed, I had to put this in. Nothing here is related to any company. Everything is my own opinion and public information. So this shows the evolution of the microprocessor in the last 53 years. It's a little bit crowded, but it presents in a compact form pretty much all the information. So it started in November 71 with Intel 4004, a processor that had only 2300 transistors, which is not a lot. Clock frequency, I believe, was 750 megahertz. The technology it was built on was 10 micrometer. It was a simple chip with only 16 pins, a 4-bit data bus, and 12-bit of addresses. And we have one computer that has been built with this chip in our expo outside here. Soon after that, Intel 8008 followed, just a couple of months later. The main difference was this one was an 8-bit data path. It got 2 extra pins, but in a sense very similar to the 4004. Then we got to Intel 880, which was hugely successful. And also in Romania, many computers have been built with 8080. So this one came out with 40 pins, which is much better package. You have both address and data at the same time. You don't need to time multiplex. So you can get much higher performance. In the meantime, there are some other companies building microprocessor. One of them was Motorola 6800, running up to 2 megahertz, also an 80-pin package. And then MOS technology, that was a hugely successful microprocessor. Why? Because it was one of the cheapest one that came around. It was built by the same engineers that came from Motorola. And the 6502 was part of Apple II, was part of Nintendo, was part of Atari, and many other things that have been built at that time. And then the next thing that was very well known to us is Zilog Z80, which came out in '76. The big thing about it was backward compatibility with 880. So pretty much everything that was running before we could run on Zilog. But it has a bunch of new features. And also just a single voltage, plus 5 volts. It was hugely successful. And then it took Intel about 2 years to get to x86, which is a 16-bit microprocessor. And that's when the PC revolution started. And fast forward, one of the latest chips announced is Apple M3 Max, which came out in October last year. It has 92 billion transistors. It runs up to 4 gigahertz. Technology 3 nanometer, pins many thousands. And database and address bits, you cannot really count them because there are so many of them, so many buses. And the table below shows what happened in those 52 years. So it was this exponential growth. I don't think we ever seen in any other industry. So first of all, the number of cores. We started with 1 core. Apple M3 has close to 10,000. But these are applications that you as a user can use them and program them. And there are different types. There are 12P, comes from performance cores. Then there are 4 efficient cores, which are much smaller, much more power efficient. So most of the time when the device is not always on, only the E cores are being used. Then we have 40 GPU processors that work totally independent. And each one of them has actually 128 ALUs. So only there you have like more than 5,000 processors. In addition, you have 16 neural engines. So these do multiply, accumulate. And each one of them has 256 packs. Besides these 9,232 processors, there are many more that are not really visible, that are used to control the hardware and do certain real-time functions. Regarding the transistors, so it went up from 2300 to 92 billion. It's a factor of 40 million times in 52 years. The clock frequency from 750 kilohertz to 4 gigahertz, another factor of 5,400. Instruction per cycle. So in the past, you need multiple cycles to execute an instruction. For the 4004, I believe you need at least 8 cycles to execute an instruction, because you have to go through multiple cycles to get the data and send out the address. Currently, you execute about 8 instructions every cycle, and these are not 8-bit, are 32-bit. So another factor of 64. The geometry. So it was 10 micrometer, 3 nanometer, another 3000x. Memory size. 4004 has 12 bits, 4K maximum addressing space. We are now 128 gigabyte. And actually the Mac Pro comes out with this configuration. Another 33 million X. Memory bandwidth. 4004, I think it could read about 100 kilobytes per second. Now we are at 400 gigabytes per second. And this is really needed when you go into high-end gaming, or for AI, artificial intelligence, or for video editing, professional video editing at high resolutions like 8K. Media engines. So in the past, they had just a CPU, but now the processors actually, it's system on a silicon. So besides the CPU, you have a bunch of other things, specialized processors for certain things. For example, the video codecs, when you do real-time encoding, decoding, and this goes, to resolution 4K, 8K, 120 frames per second. ProRes, which is a standard for professional video editing. And when Apple shows the new products, you have, it shows you can do 12 streams or 20 streams real-time 8K resolution. ISP, image signal processor, so this interface to the camera that you have to do all kinds of corrections and processing, and then a bunch of pixel processors. So it was a complete revolution. So many talk about Moore's law. So Gordon Moore was one of the founders of Intel, and he realized that every 18 months initially, then he corrected to 2 years, the density goes up by a factor of 2x, price goes down, frequency goes up, power consumption goes down, so it was a virtuous cycle. You just have to wait, and you get a much better processor. And this shows the evolution, number of transistors for CPU. So this diagram starts in 2020, so it goes up a little bit. So it starts here with 4004 and then all the other ones. But this is just at the high level, because one thing that happened, the cost per transistor doesn't go down anymore. So right around 7 nanometer, you get more transistors, but the price per transistor being constant, actually the price goes up. So this is a huge problem. This is a discontinuity that's happened that never was before, and people are not counting on. Right now we are here at 3 nanometer, and new designs are being done in 2 nanometer. And people expect to get some improvements later on, but so far nobody knows what happens. So regarding the scaling, so this is a thing that is similar to Moore's law, then our scaling, which sort of saying that the power density stays about the same. And yes, that did happen till about 2005, 2006. So you still get more transistors per die, but it comes because you have multiple cores. You don't get a single CPU that is much larger, but you have many of them that you have control. Another problem here is the power consumption. So it flattened. Frequency. So about 2005, we got the first 5 gigahertz microprocessor, and then it's flat. You can't go higher anymore. And this is single thread performance. So if you have a program that runs on a single CPU or single thread, there's a little bit of improvement. This is because of microarchitecture improvements, but it's not a lot compared to the rest. So going forward, yeah, we just can add more cores and do architecture improvements. So this is a big discontinuity. It's a problem, but as any problem, it comes with opportunities. So this sort of summarizes what happened over the last 52 years. But if you look inside the microprocessor, the underlying principles and functions are pretty much the same. You have arithmetic logic units. It's not only one, you have thousands of them. You have registers, you have memories, they interconnect, which becomes sort of the more important thing. Clocking, input, output, and that's pretty much it. And the question comes, how are you going to design such a chip, 92 billion transistor? How you can do it? And divide and conquer. You slice it in smaller pieces. Everything is hierarchical. You start from the top level, figure out what you need to solve at the system level, and you go down. There's a lot of parameterization happening. So with the same design that you parameterize to go into different products, like a high-end computer, go into a tablet, go into a phone, go into the watch, or in airports, but it's pretty much the same design. You don't have to do it twice. And reuse. What is extremely important is architecture and microarchitecture. How things work at a high level. You have to determine the use cases. What problem do we need to solve? That's how you start. To figure out the data flow, because data movement is more important than computation. What performance do you need? How much bandwidth? So from that one, these are the top level requirements from which you go down and figure out how to implement it. So again, system on chips are huge, but they consist of building blocks that are locally optimized. And on such a chip, there are tens of thousands of engineers working at the same time. So a single fab, how you manage that, how you put them together. Another thing that people say, oh, right now, because you have so much memory, so much of this, you can write sloppy software. No, it's not the case. Actually, there's a lot of data and code compression that is being used. Because memory is never enough, bandwidth is never enough. And pretty much all the latest CPUs for all the manufacturers, they use compression. Mostly on the data, but also code compression. Most of the time it's lossless, but some content like audio and video, they allow lossy compression. I don't know how many you recognize this. It's Apple Vision Pro. It has two big SoCs. And this shows here it's a trend that will follow. So until now, the trend was to integrate everything, to have a single SoC that does it all. But for all kinds of reasons, economics especially, yield, how many of the chips are good, a disintegration follows. So you're going to use multiple chips to solve to have a particular system. So this is a heavy engineered product. It has 14 cameras, a bunch of sensors. It was very fun to work on it. The biggest achievement is the latency. So it's what's called motion to photon latency. The eye can move extremely fast, and the brain expects in at most 15 milliseconds, you're going to see the results, the new image. And if you don't, even if you don't, can point out, oh, that line is not correct, but it gives you dizziness. Something is wrong. So you have to bring the latency below 15 milliseconds. Now, what means 50 milliseconds? If you have a camera that has 60 frames per second, that's already 16 milliseconds just to capture a frame. For Vision Pro, the motion to photon latency is 12 milliseconds. And what do you need to do those 12 milliseconds? You look at something, you have to detect where the eyes are going. Then based on that, to generate a new frame, and because the screen is so close to the eye, there are a lot of geometric distortion, chromatic aberration that you need to compensate for. So in at most 12 milliseconds, you have to have the new image there that looks correct. So regarding the state of microprocessor, so I'm focusing now most on microprocessor because it's sort of the brain of the computers. So in the past, people talked about instruction set architecture. That is very important. But over the years, you have different ISAs, x86 that are still in existence, MIPS that have been heavily used in the past, and they are still, but they are not anymore what they have been in the past. Spark was a company, Sun Microsystems, that was acquired by Oracle. Motorola 68000, that also got many products. PowerPC was also inside Apple. ARM, which is heavily used right now. And this is new open architecture, X5. Actually, it's not quite new. It's been around for 7, 8 years. But it's open source. And the thing is, it doesn't really much matter what instruction set you use. There is a 10, maybe at most 15% difference. What difference it makes is the tools, the compilers that you have. Then why some of this architecture made it to the market, or why they have been successful, is first of all market needs. All this development costs a lot of money, so you have to have a return, otherwise you don't get money to build them. You need good management. And the company that succeeded had a very good management. Those that don't, they had a bad management. And execution. Like anything, no. If you don't execute, nothing matters. Good examples about all these things, market needs, good management, execution, are NVIDIA, which is one of the biggest companies currently, Apple, Avago, which is sort of a special company, came out in Singapore, and they grew through acquisitions. They acquired LSI Logic, which was my first employer in the United States. They took their name, LSI Logic. They acquired then some other companies, including Broadcom. They took also their name, and now their market cap is close to 1 trillion, and probably by the end of the year, they're going to be above 1 trillion. TSMC, Taiwan Semiconductor, is the best. Pretty much all our high-end CPUs are built there. About 60% of all chips are built in Taiwan. And the sad story is Intel. Intel, which in 2020 had a market cap of about $500 billion, now it's only about 150. They lost so many trains. In the late 90s was the Intel duopoly, Microsoft and Intel. Right now, they have huge problems. They have been overtaken by TSMC in the manufacturing. They've been overtaken on CPU performance by Apple and some other companies. So, you know, that's life. So a thing that happened over the last 50 years, you know, hardware has to be fast and simple. You don't have to overcomplicate it. And the control, the dependencies are handled in software or in firmware, low-level software. Compiler and tool change are essential. I mean, you don't write anymore in assembly. I mean, you write in very high-level languages, and the compiler is critical how you generate optimized code. So, as we've seen, it was this Moore's law that the industry relied on for way too long, which in a way inhibited innovation, because you knew, no, next 2 years I'm going to get the next process, it's going to be faster, cheaper, higher performance, but not anymore. And this was an exponential law, so like anything exponential, at some point has to stop. But it did around 2006. And as I said, like any problem, it brings many opportunities. And for a while, at least in Silicon Valley, it seemed that, you know, hardware was a dead thing, you know, that everybody wanted to do software. But not anymore. I mean, we are witnesses of computer architecture renaissance. Now, because you don't have any more Moore's law, you are forced to think harder, to find better solutions to the problems that need to be solved. So what's next? As I mentioned, in the past, it was about integration. Have a single chip, cost was cheaper, power consumption lower, but because of yield problems and cost, Actually, there are a couple companies already do this disintegration in the high-end CPUs. And it's going to happen more and more. They call it chiplets. One of the biggest challenges is power consumption. I mean, power density is getting higher. AI is, the new kid on the block. Everybody wants to be there. But at least now it's a brute force solution, and it's not sustainable. A few months ago, Jensen Huang from NVIDIA, he had a talk at NVIDIA Developers Forum. And I was a little bit disappointed because the only thing he was saying, oh, we need bigger CPU and more powerful CPUs, GPUs. And that's about it. In the past, they were building GPUs for the gamers, which took like 500 watts or 1 kilowatt, and they got to liquid cooling. Now it's not enough. They build the data center. And their chips now go into a rack, and it consumes 50 kilowatts. And they claim, oh, this is much better compared to competition. Yes, it is, for now. But if you look at power consumption, efficiency, and again, this is not sustainable. It will stop at some point. So overall, we need to move with less. Get to higher performance, but with lower power. And how we get there? These are some tendencies that are starting to become more and more important. So far, nobody was looking very seriously into them because, you had Moore's law. But now they do. So first of all, higher level of abstraction. Currently, how you program a CPU, you tell add, multiply, load, store, and some of this stuff. Maybe you have DLIW, they do multiple instructions per cycle, but it's pretty much the same. It's spoon feeding every single bit. So you have to tell it something much higher level. Solve me this problem. And to do it in a concise way and precise way, such a computer knows how to do it. You're going to have domain-specific processor. So you started with the CPU, central processing unit, but then you got to the GPU for the graphics. Then you have the neural engines. So these are domain-specific processors. They do very well a certain class of problems, but they are not generic. And more will follow in this line. Data locality, especially also for AI, because they deal so much data. You have to keep it locally, because that's how you reduce power consumption. These days, for the last 5 or more years, data movement is more costly relative to computation. Function-based programming. I remember when I was a student, I had a class with Professor George Stefan, functional electronics. And, it's an old idea, but it's still actual. Caching, very important, hierarchical caching, multiple levels. Currently, we are at like 3 or 4 levels of caching. Another thing is processor chaining. Not that you do something, put it in memory, but go from one to the next without touching external memory. Okay, now getting a little bit more into marketing or business. So what drives the technology? First of all is disruption. So you have to destroy the old and bring something new. That's the basic idea. Regarding the process technology, these are the companies that have been leader in building chips. A long time ago it was IBM, but not anymore. For a while, for many years, it was Intel. They have been one generation ahead of everybody. Then Samsung was for a while. Right now, TSMC is a clear leader. They left everybody behind. Both Apple and NVIDIA, they rely 100% on TSMC to build their chips. So everybody hopes nothing will happen to Taiwan. A category of products are the game consoles. It started with Atari, we had Sega, Nintendo, gaming PCs, which are still around, and then dedicated machines like Sony PlayStation with multiple generations, Microsoft Xbox. But lately, more and more it gets into a mobile phone because they have GPUs that have quite a good performance, and they are very handy, like with the camera. There are very few people that have large cameras, just the professionals, but otherwise, everybody's using the phone. Same thing happens in gaming, mobile phones and tablets. Certain category of products. So it was PC, that built Silicon Valley. It was Wintel duopoly, Wintel and Microsoft. They are making the money. Everybody else was just working. Digital still camera was for a while that was driving the market. SanDisk is one of the best companies. George Samakisha, he was a professor at Electronica. He was the first technical guy hired within SanDisk, and most of the technology was developed by Samakisha. Mobile space, Nokia was there for a long time. It was displaced by Apple and Samsung. And AI, which currently is NVIDIA. Another evolution is about media delivery. In the past, you have tapes and cassettes. Then you got the VHS tapes, CDs for music. Then it was a standard video CD that got a lot of traction in Asia. So were movies compressed with MPEG-1, stored on regular CDs. And there was a huge market in, I think, in the late 90s. There was also Laserdisc for a while, and DVD, which was a big change. Blu-ray, high definition. And Blu-ray is the last physical media support. So you don't go and buy a disc anymore or a tape. Everything is streaming now. And it's going to be streaming forever. I mean, there'll be nothing physical anymore. Industry disruptor. So who made a huge difference on? So there are 7 categories. Are the pioneers that came first. First of all, was Shockley Laboratories, and they had an office in Mountain View. I think they started in '56. They built a transistor. Then most of the people left. The traitors ate. They went and founded Fairchild, which was a company with a long history. It was Zilog, that we all know about. Digital Research, that is very familiar here, that built a CPM operating system. Gary Kildall is the guy responsible for it. Then you have some of the founders that made Silicon Valley what it is. Hewlett-Packard, which was initially there. Apple, that was the initial phase with Steve Jobs. Intel, Microsoft, the PC revolution. Cisco, networking. Qualcomm, communications. Then you got the dot-com era, so for the late phase. Many companies went bust. They didn't have any way to make money. But there are some that remain, like Amazon, eBay, Yahoo. Yahoo to a lesser extent, but Amazon, it's one of the biggest companies. Social media. So that's sort of after the dot-com bubble. Google, Facebook, Instagram, ByteDance, which actually has TikTok. So it's a little bit different compared to how it was before. It's not anymore building product, but building, interaction. And then the latest tech companies that made a big difference, Netflix, which is a special company. Netflix is the one that they had 3 revolutions or 3 disruptions that they did. First one, when they realized that the VHS tapes are going to go away, so they came up with this model to send you through email a CD, a DVD, and that's how they went public. Then a couple of years later, they realized, but broadband is so much better now, and they went into streaming. That was the second revolution. The third one is original content. So they took on Hollywood to build their own content. Also Apple does to some extent. Then you have Apple after 2007, after the iPhone came out. Tesla, which also it's an amazing company. In 2000 to 2020, the stock went up 10x. So if you invested $1,000 in January, you had $10,000 at the end of the year. In the meantime, it slowed down. Why? Because there's competition, especially from China. But they did, there was a company that at some point was valued more than $1 trillion, more than Toyota, Honda, BMW, Porsche combined. Amazing. Broadcom that I mentioned, Avago, Microsoft, which compared to Intel, had a completely different evolution. So Bill Gates, he left in 2000. At the time, Microsoft was like $500 billion. Then Steve Ballmer came on, which was sort of a little bit flaky. He was booted out. But then Satya Nadella came in, the latest CEO, which was a very sharp guy. They got in the cloud. They have a special deal with OpenAI. So now it's the largest company, valuation-wise, like $3.3 trillion. And NVIDIA, it's riding the AI wave. Okay, real technology evolutions. What are the latest trends? So it goes from the mobile owning to renting, everything, including content. Also, everything goes from physical to virtual. So in the past, you buy a product, it was yours. Now, everything becomes virtual. So there was a company, I don't know if you remember, in 2005, Second Life. You can build, a virtual world and build things. I'm not sure it was popular here, but it was in the United States. The social media companies, the metaverse, the robots, AI. So everything becomes more and more virtual, artificial. You can doubt, is it useful? Does it cause more harm than good? It remains to be seen. Another thing that characterizes high tech, you need capital, you need money, plenty of money. So you have these venture capitalists that, there are people that know how to raise money, and they give you, okay, I can give you $10 million, give me 30% of your company. And then you run out of money, oh, I need another 10 million, 20 million. Okay, I can give you, but we have to give you another 30%. So by the time the company goes public, you already give out like 80, 90% of the company. Typical, not always, but that happens many times. And they have a herd mentality. When something they believe is hot, everybody wants to invest. Or there are some other companies that might be very good company, but for some reason they don't invest. Then how things evolve. So being part of a herd mentality pays off only if you are at the beginning, if you are among the ones that drive the herd. But if you are toward the tail, you're going to lose your shirt. In general, disruptors and trendsetters are contrarians. They don't go with the herd. They think it through and do something different. And those are that build big companies. A good example is the consumers market. For many years, in the 90s, early 2000s, no VC wanted to invest anything in consumer related. So you cannot make money, margins are so low, you're going to be eaten by China. The counterexample is Apple. They went head on into the consumer. And it was a field that was completely uncovered, good execution, and there where they are. Artificial intelligence. So there are many opinions about it. Everybody wants to talk about it. My personal opinion, it's a bubble, similar to the .com. So it doesn't mean everything is bad or everything is good. It's somewhere in the middle. So a lot of capital will be wasted. But some major companies will emerge. NVIDIA is just one of them, but there'll be a few more. So indeed, there is a resolution, but it's not going to solve all the problems that we have. AI, in a sense, is an ultimate copycat, because what they do, they analyze content, data, extract all kinds of parameters, and based on that, they generate new thing that is based on the old stuff. So it's like copyright infringement. It's like copying. Intellectual property appropriation. Hollywood has a problem with this. The actors, because they steal their voice and all of that. It's a huge problem. My opinion is that humans will not be replaced by robots. There will be jobs that will be dislocated. Those jobs that, anyway, didn't require a lot of special thinking. And I think Federica is going to touch on this issue. What is the difference between AI and human intelligence? So, there are two classes, followers versus leader. And as everywhere, you have just a few leaders. Everybody follows. What do the leaders? They don't fight the trend. You try to understand it. You try to find the Achilles heel, what the entrenched players are doing wrong, and then you have to disrupt the status quo. So all the large companies in Silicon Valley has been built that way. Now a few things about high tech and Silicon Valley. It's a special place, as we all know, and it's responsible for most of the economic growth in the last few decades. At least that's the case in the United States, and I believe pretty much everywhere. I mean, everybody has to have computers, everybody goes online, everybody has a phone. You pay the parking with the phone, you know, everything is based on high tech, which if you go back 20, 30 years, nothing was about this. But it's a ruthless environment, you know, so huge amounts of money, many people that are very hungry and eager to get a piece of it. So at the surface, everything is nice and dandy. But, you know, there's competition, extremely hard competition. Regarding startups, there are so many of them. You know, like you go, like the nice ladies, they go to Hollywood, they try to be actresses, and just a few are the ones that are renowned. The same thing in Silicon Valley. It's only about 10% of the startups that survive, that do something meaningful. The rest go under. And less than 1% that are home runs. I mean, companies that really make it, that go public, valuations of above $10 billion or so. And to close it, there's a guy, Andy Grove. He used to be CEO of Intel. He came from Hungary. He left in '56. So he is one of the guys in Silicon Valley, you know, good parts and bad parts. Good parts in the sense for Intel, what he did for Intel. But, you know, again, competition. I mean, he did everything he could to stay above. So he had a saying, only the paranoid survive. So to some extent, you know, it's a little bit pushed, but I think it reflects what's happening there. Okay, I think that's what I had.
May I have a question for you? How is your prediction about the technology? How many steps we will have in the digitalization? We are 3 nanometers?
Yeah, so it's getting very close to that. In the past, people predicted it's going to stop around 5 nanometer. Now, the latest processors are 3 nanometer. Pretty soon, you're going to get 2 nanometer on the market. TSMC is working on 1 nanometer that's also commercially viable. But again, it becomes more and more costly. Actually, the cost per transistor, when you go to 2 or 1 nanometer, actually the cost goes up.
Okay, but it's not only costly, but it's impossible. Because
yeah. I mean,
how many atoms?
So you are already at, I don't know, a few atoms.
Yes.
So there's not much more you can go down.
Yeah.
And so the reliability is pretty bad. So there is a lot of redundancy. I mean, when you have 92,000 transistors, for sure a few will be bad. So there are all kinds of mechanisms to shut them down and to replace them, to have bypasses. So there's a lot of redundant logic to take care of that. And it can do that to some extent. The same thing happens in the flash memories, that in the past was 1 bit per transistor, now 2 or 3 or even 4 bits. And, you know, it can be flaky fairly soon. So they have a sort of redundancy, error correction. It's getting harder and harder, yeah.
It's coming to an end.
Yeah, it does. But I think another 5-10 years still it's going to go this way. Okay, thanks a lot. So we have another break, about 30 minutes, and then we're going to continue with the main event. Hopefully everybody will be back. Thank you.